Welcome back. In this video, I'm going to solve exercises 8 to 10 of chapter 3. So they are exercises mainly on the open mapping theorem and its consequences. Okay, we start with somehow difficult result. Actually, difficult. This is a bit difficult. But it's very important because it illustrates a typical reasoning, a standard reasoning in analysis. Okay. So we have two Banach spaces E and F so E is equipped with a norm that I call norm sub E, and the norm on F is denoted by norm sub F. Okay, and we have a bounded linear map T from E to F, whose range is closed and his kernel is finite dimensional. Okay, so this is a very important property actually. And we have another norm on E, okay, which is weaker than the original norm. So this norm is denoted just by an absolute value symbol. This is possible actually. Okay, we could denote by norm 1 if you like, if you don't like the symbol, but this is not absolute value. This is another norm. Okay, so we have to prove that the original norm of E is less than a constant times this new norm actually. So this is, as you may check, a norm, another norm on E. So, and by the way, since T is bounded and this norm is less than a constant, so you can prove that actually this norm is weaker than, so actually this inequality tells me that the two norms are equivalent. Okay. So, hence argue by contradiction. Okay, this is really very typical. So first of all, when we look at T as a map from E to its range, we get a surjective map. Okay, so can use the open mapping theorem actually. So we don't care about the rest of F. We just care about the image. Okay, so we can consider T as surjective. Okay, this is true for any map. Okay, so when we restrict the range or the target space to the range, we get a surjective map. And now, since F is Banach is complete and R of T is closed, then R of T is itself a Banach space, as you know. It's complete. Okay. Now, suppose that this is not true. Okay. So what does it mean there exists C such that for all X this is true? So if you negate this, you'll get for every C, and there exists X such that this is bigger than this. So you take C equal 1, 2, 3, 4, the integers, or any sequence going to infinity. Then for each constant, you'll get 1x. So we called it xn. I called it here actually un. Doesn't really matter. Okay. So this is just the negation of this inequality in terms of quantifiers. Okay. So there exists becomes for all, and the for all becomes there exists. Okay. So this is really something that you should master. Okay. So in particular, this is un cannot be 0 because 0 cannot be okay, because this is bigger or equal than 0. So therefore we can divide by the norm of un, the norm E to be precise, and by homogeneity of this norm and T and the original norm, when we divide by T, you can write this as T of un over its norm and this as un over its norm. And if you put xn to be this un over its norm in E, then the norm E of xn is just 1. This is the norm E. Okay? And then we divide by n, so we get txn in norm F plus absolute of xn is less than 1 over n. So in particular, this guy is less than 1 over n, and this guy is less than 1 over n, and so both terms tend to 0. Okay? Okay, now, since T is surjective and we are working between Banach spaces, we can apply the open mapping theorem, which is equivalent to saying that the image under T of the open unit ball contains a ball of center 0. Okay? And so, as you may check by linearity of T and the standard operations on balls, if you multiply by 1 over n, if you like, take the homotopy of ratio 1 over n, then the ratio here becomes 1 over n. Here we have T of 1 over n, and therefore, yeah, so Same thing actually. So if you like, you can divide by c first. So b01 is less than t of b01 over c. Okay? Or you can, if you don't believe me, you can just take an element here and prove that it's here. If you take an element here, let's call it anything, z. The norm of z is less than 1 over n. So nzc is less than c. So it's here, then so on. Okay, so just write the. Okay, now by the previous inequality, the norm of txn is less than 1 over n. So txn is here. Therefore, it's here. What does it mean that it's here? It means that it is in the image. So txn is equal to t of some yn, where yn is here. Right. So that's what I. Okay, now let Zn be xn minus yn. So why this? Because txn equal yn, so means that txn minus yn is 0. So xn minus yn belongs to the kernel. Okay, so I can write xn as yn plus zn, where zn is in the kernel. So okay. Therefore, now I just write zn equal xn minus yn. So, and I apply the triangle inequality twice. So the norm of Zn is less or equal than the norm of the difference, which is less or equal than the norm of Xn plus the norm of Yn. And the norm of Xn, as we said in E, is 1, actually. And the other way around, the norm of Xn is bigger than the norm of Xn minus the norm of Yn. This is the second form of the triangle inequality. So we get this double inequality, if you like. And since yn tends to 0, because it's less than 1 over nc, then this term, this number tends to 1, and this sequence tends to 1. So the norm of Zn tends to 1. On the other hand, you are almost done. The second norm on E of xn is less than 1 over n, as we observed. Therefore, when you apply the triangle inequality again, because Zn is just xn minus yn, so the norm of Zn, second norm of Zn, is less than the second norm of xn plus the second norm of yn. So I get 1 over n plus 1 over n. And once again, I know that this so by the fun, because the second norm is weaker, so it's less than a constant times the norm of yn. So in particular, this also tends to 0. So Zn, the second norm tends to 0. And this is the contradiction now, because the norm, the first norm, let us call it. So I would call this second norm, and norm E is the first. So the norm E of Zn tends to 1, and the second norm of Zn tends to 0. So this means that they cannot be equivalent. Okay? It's not possible to have first norm of Zn is less than a constant times second norm of Zn, because this will, if this tends to 0, this will tend to 0 as well. Okay, and I know that on any finite dimensional space, all norms are equivalent, right? So this is a contradiction. Okay. It's a bit lengthy, but you should be exposed to such kind of reasoning because it's used often in analysis. Okay. Second exercise, the exercise 9 is a little bit easier and more concrete. So here we take a specific normal spaces. So we take the space of all continuous functions from 0, 1 to r, denoted by E, and I equip it with the supremum norm or the maximum norm or the norm of uniform convergence, same thing. And I consider this norm subspace, so F is a subspace of E, but it's a normal space on its own. So it's the set of all continuously differential maps which vanish at 0. Okay? And I also equip it with the maximum norm. And now we consider the linear operator L defined by the integral of U. So if you like, if U is a function, L of U is just the antiderivative of U, which vanishes at 0, because when I put t equals 0, I get 0. Right? So this is in terms. So this is the meaning of. So this is what we call an integral operator. Okay. So U is a function and LU is a function. So LU is an element in capital F. Okay. We know that the antiderivative actually is C1 by the fundamental theorem of calculus, because the derivative of LU is just U. So if U is continuous, so LU is C1. So LU is really in F. So first question, we have to show that L is bounded. Second question, we have to show that L is bijective and find its inverse. Then show that the inverse is unbounded. And does this contradict the Banach isomorphism theorem? Okay, because the Banach isomorphism theorem states what? That if a linear bounded map acts between Banach spaces, then its inverse is automatically continuous. Okay. Okay, so first of all, since we are taking the maximum norm, we could write norm infinity if you like, to be precise, but since we don't have any other norm, just write the norm. So this is the maximum, so it's bigger or equal than the absolute value of US for every S in 0, 1, and therefore I can integrate now from 0 to t. And since t is between 0 and 1, we get that the absolute value of L of U, so the antiderivative of U at the point t, is less than the norm of U. So when I take the maximum over t, I get the infinity norm of LU is less than the infinity norm of U. So this proves that L is bounded and its norm is less or equal than 1. But actually, we can prove that the norm is exactly equal to 1 because we just take the constant function equal to 1. Okay, so this is easy. Now, to find L minus 1, we have to solve the equation LU equal V. What does it mean, LU equal V? It means that LU is an antiderivative of V, or U prime, or U equal V prime. Same thing, actually. So this equation is uniquely solvable, actually. And U is just the derivative of V. Okay, so this means that the inverse, so L minus 1 is just the derivation operator, okay, that I call T. It maps from F into E because in order to differentiate, I need differentiable maps. So to each element in C1, so to each function which is continuously differentiable, I associate its derivative. So, right. Okay, why T is unbounded? And I gave you a hint. We consider the sequence sin nt. Its maximum norm is 1, as you know, because the sign has a maximum value at 1, and it's achieved at the point, for example, 1 over pi over 2 plus n pi. Okay. And its derivative is just n cosine nt. And once again, what is the maximum of this function? It's enough to take t equals 0. When t equals 0, you get n. So this is, and the maximum value of cosine is 1. So the norm of tun is just n, actually. Okay. And this precisely means that t is not continuous. So un is bounded, but its image is unbounded. Okay, and this contradicts the continuity of, so t is not continuous. Okay, so we know there's an equivalence between saying that an operator is bounded or continuous and maps bounded sets into bounded sets. So here we map a bounded set into an unbounded set. Okay. Now, this does not contradict the Banach isomorphism theorem because the assumptions of the Banach isomorphism theorem is we have to assume that both spaces are complete. Now, E is complete, but F is not complete. Okay. Why F is not complete? This is why. This is one proof. Consider this sequence: radical of t squared plus 1 over n minus radical 1 over. Now, I subtract this just in order to make sure that W is in F, because Wn of 0 is just radical of 1 over n minus radical of 1 over n. So this is a sequence. Of course, it's C1, because we are away from 0. So this function is C1 and vanishes at 0. So Wn belongs to F. And Wn converges to radical t squared, which is absolute t. And you can prove that convergence is uniform. So it's convergence in the norm of F, in the subnorm. Recall that uniform convergence is precisely convergence in the subnorm. This is why we call it the norm of uniform convergence. You check that actually, it's not difficult. Take a paper and a pen and do that, because I may ask you such things in the exam. Okay, you should be able to prove that Wn converges uniformly to radical t. So you write Wn of t minus absolute t in absolute value. So you just subtract minus radical t, and then you multiply by conjugate expressions and so on. You should be able to do that. Okay, so and now the limit actually is not differentiable, so it's not in f. Okay, so f is not closed, and therefore cannot be complete. Okay, so in principle you encounter such things in second year. Okay. Okay, so now next exercise is a counterexample of a remark that I said. If an operator is if a sequence of linear bounded maps from two Banach spaces between two Banach spaces converges pointwise, it doesn't mean that it converges uniformly. Okay, I said this remark in corollary 3.1 of the Banach-Steinhaus theorem. Right? So this is a counterexample. So I have to give an example of a sequence of linear bounded maps converging pointwise but not in the operator norm. So we consider the space or all the fundamental space of all continuous maps from 0, 1 to R with the supremum norm or the maximum norm or the norm of uniform convergence, same thing. And we consider this sequence of maps. Okay, so Tn of u is just the integral from 0 to 1 of sine n pi t times ut. So I'm integrating u of t against sine, so just a kind of antiderivative, but of this. Okay, so just, it's not an antiderivative, but okay, so we have to show that Tn of u tends to 0. For this, there's a very important fundamental result called the Riemann-Lebesgue lemma that I will explain now. And then we have to compute the norm of Tn and conclude. Okay. Now let us recall the very important Riemann-Lebesgue lemma that you may have encountered. If you didn't, it's okay. I will explain it. So it states the following: if f is a continuous function on a closed interval AB, or more generally, if f is an LP that you studied last year for some p between 1 and infinity, then the integral of f of x times sine lambda x and the integral of f of x times cosine lambda x as lambda tends to infinity is 0. I'm not going to prove that, but there are at least 3 ways of proving that, if you like. The first way, you can use the elementary theory of Fourier series that you learned in second year. And you can also use the theory of Fourier transforms that you learned last year. And I have an exercise actually where we prove that. Or you can use an approximation argument, because a function in C or in LP can be, consider first the case of a continuous map. A continuous map by the Weierstrass theorem can be approximated by polynomials and therefore by C1 maps uniformly. And now if you assume here that f is C1, you can integrate by parts. And when you integrate by parts, so you have to differentiate f and integrate sine lambda over x, you get cosine lambda over lambda. And when you do this, you find that you get something that tends to 0. Same thing for here. And then you may use the approximation argument. Okay, so if this is true for C1 maps, it's true for C maps, for continuous maps. And we have something similar in the LP norm, actually. Okay, so this is the idea. Okay, so therefore, what we said here is just, so in particular, here I take lambda equal n pi, and a equals 0, b equal 1. So this tends to 0. Okay, so the limit operator is just the 0 operator. So Tn converges pointwise to the 0 operator, but not uniformly. Why? This is a little trickier, because there is an exercise in chapter 0, exercise 10, that tells me that there is a very simple formula of the norm of the operator Tn. It's just the integral of the absolute value of sine n pi. So in general, if we have, if if t is the integral from 0 to 1 of g of t, u of t, then the norm of the operator is just the integral or the L1 norm of g. Okay, so this is the L1 norm of sine and pi t. Now, how to compute that should not be difficult for you. You should be able to do that if you are majoring in math. Okay, first we do a change of variables to get rid of the n pi. So we set n pi t equal s. Okay, then we do the usual change of variables. So t equal 1 over n pi s. So I get to divide by n pi, and the 1 becomes n pi. It's very easy. So when t equal 1, this becomes n pi. And now how to compute that? The sign changes sign when it goes from an interval to an interval. So from 0 to pi is positive, from pi to 2 pi it's negative, and so on. So I have to split that into intervals where sign has a constant sign. Okay, so I write this as the integral from 0 to pi plus the integral from pi to 2 pi, and so on. But since I'm taking the absolute value of sine, the integral of the absolute value of sine over an interval of length pi is just actually 2, right? For example, the integral from 0 to pi of absolute sine is just the integral of sine, which is minus the integral of the, so it's minus cosine from 0 to pi, which is 2. And similarly, from pi to 2 pi, you'll get minus sine, so you'll get so on. Okay, you do that. So it's easy to see that this integral is just 2. So I'm summing 2 n times. So I get, so this sum is just 2n. So I get finally 2 over pi. And therefore, the norm of the n does not tend to 0. Okay, so this is just to illustrate the remark that you have to be precise when you deal with convergence. You have to precise in with respect to which topology or with respect to which norm, because you should know that there are in math and analysis there are so many kinds of conversions for functions and operators. You have pointwise conversions, uniform conversions, strong conversions, weak conversions, conversions in probability, conversions in so okay, so we have to be precise here when we deal with the notion of conversions. Okay, so this concludes this video and the chapter as well. There are more exercises actually that I didn't solve, but you can read the solution. You can solve. You are encouraged to solve them on your own to test your understanding. But the solution also are available on my website. So this concludes chapter 3. And in the next video, I'm going to start the very lengthy and important chapter 4 that contains so many information. So we'll need some time to cover it and digest it. Okay, so next chapter will be the most difficult one in all the course. So thank you for your attention and see you next time.